Welcome back to our course, Fundamentals of Operating Systems, based on the text Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Cagney, and Peter Galvin, published by Wiley Publishing. During the last two units of Module 2, we've been talking about processes, that is, the work being done. When we use terms like CPU, memory, devices, and so forth, we're talking about things, the physical things we discussed in the first module. But a process is the work being done by those things. It's the meat of the whole discussion. We learned that a process is a unit of work, and now we're entering our third unit on the topic. Now let's take a moment to talk about the real point of these discussions of processes. By now in your journey toward a degree in information systems, you should have learned already that the two main goals of such systems are to be efficient and to be effective. So what's the challenge? Well, if you think about it for a moment, you might realize that efficiency and effectiveness may very well be contradicting goals. When we strive for efficiency, we are trying to maximize the performance of our system by reducing redundancy and eliminating all unnecessary steps. When we strive for effectiveness, we're trying to make the whole system more reliable or user-friendly, let's say. Make it more understandable. Make it fair. These two goals, efficiency and effectiveness, can clash with one another. Just as a brief introduction to this unit, let me use the subject of giving access to the CPU to these ready processes. In fact, that is the topic of this unit. How shall we implement this access? In other words, who gets the CPU first, and then next, and so on? Well, how about first come, first serve? What could be fairer than that? Oh, but wait. Would that be efficient? Let's say that we have 10 processes waiting for the CPU. Now remember, a modern CPU can perform billions of instructions a second, so it's conceivable that many of these processes, once they get the CPU, will almost immediately give it up and move on to their next task. On the other hand, there may be other processes that are doing nothing but calculations, and because of that, they may never give up the CPU unless it's taken away from them. Now back to our first come, first serve scenario. What if the CPU hog happens to be the first in the line? Well, then everyone else would have to wait and keep on waiting. Do you think that the other 9 processes and the users running them would consider this approach effective? Well, let's get into the unit and find out how we deal with this issue. In a system with a single CPU core, only one process can run at a time. Now, we've talked about that a number of times. Other processes must wait until the CPU's core is free and can be rescheduled. The idea is relatively simple. A process is executed until it must wait, typically for the completion of some input-output request. In a simple computer system, the CPU then just sits idle, waiting for that input-output to complete. All this waiting time is wasted. No useful work is accomplished. Now that doesn't sound efficient. With multi-programming, we try to use this time productively. The objective of multi-programming is to have some process running always to maximize CPU utilization. Several processes are kept in memory at one time. When one process holds on to the CPU, the operating system takes the CPU away from that process and gives it to another process. This pattern continues. Every time one process has a CPU, another process can take over use of the CPU. On a multi-core system, when we have several CPUs on one chip, this concept of keeping the CPU busy is extended to all processing cores on the system. Scheduling of this kind is a fundamental operating system function. Almost all computer resources are scheduled before use. The CPU, of course, is one of the primary computer resources. Therefore, its scheduling is central to operating system design. The success of CPU scheduling depends on an observed property of processes. Process execution consists of a cycle of CPU execution where the job has been assigned to CPU and some sort of processing has taken place, and an I/O wait where the process gives up the CPU and waits its turn somewhere. By somewhere, I mean that a job may request another device, in which case it waits for its turn for that device. Or it loses a CPU because its time expires, and it waits for another turn at the CPU. Processes alternate between these two states. Process execution begins with a CPU burst, and that CPU burst is followed by an input-output burst, which is followed by another CPU burst, and then another input-output burst, and so on. Eventually, the final CPU burst ends with a system request, or a system call, to terminate execution, as you see in this figure. The durations of CPU bursts have been measured extensively. Although they vary greatly from process to process and from computer to computer, they tend to have a frequency curve like the one shown here. The curve is generally characterized as exponential or hyper-exponential, with many short bursts and a few long CPU bursts. An I/O bound program typically has many short CPU bursts because the process has given up the CPU for the input-output device. A CPU bound program might have a few long CPU bursts. This distribution can be important when implementing a CPU scheduling algorithm. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. Remember the ready queue? We're talking about the process manager here, aren't we? The selection process is carried out by the CPU scheduler component of the process manager, which selects a process from the processes in memory that are ready to execute and allocates the CPU to that process. Note that the ready queue is not necessarily a first-in, first-out queue. Thank goodness. Those 9 short processes would have hated that. A ready queue can be implemented as a first-in, first-out queue, a priority queue, a tree, or simply an unordered linked list. Conceptually, all processes in the ready queue are lined up waiting for a chance to run on the CPU. The records in the queues are generally those process control blocks of the processes we discussed in the earlier unit. CPU scheduling decisions may take place under the following circumstances. As you can see from this bulleted list, the first one is when a process switches from the running state to the waiting state. Examples of this could be the result of an input-output request or the invocation of a wait for the termination of a child process, something that we talked about in the last unit. Second one is when a process switches from running state to ready state. That's when an interrupt occurs. An interrupt perhaps caused by its time running out. Thirdly, when a process switches from a waiting state to a ready state, as would occur with the completion of some input-output request. And finally, when the process finishes, when it's terminating. Let's take a break right here. When we come back, we'll discuss how situations 2 and 3 are handled by the operating system. Look over your notes, take care of any business that you need to take care of, and when you're ready, come on back to lesson 2 of unit 3.